Pleasure meeting and seeing you all online. I'm supposed to press a button here, but without the mouse, that's actually not really, let me do it like this. So I don't have this window smack in the middle of my view. Yeah, so I'll be talking about dwarf galaxy archaeology, and I'll explain what that is. We continue to try to answer the big questions with tiny stars and tiny galaxies. And yeah, to get everyone on the same page, I'm going to give a somewhat lengthy introduction. I think that's important, and then I will go through two galaxy examples that I'd like to share with you. The universe obviously started almost 14 billion years ago with the Big Bang, and left behind a universe made from just hydrogen and helium. And that gas doesn't like to cool very well, can't cool very well. And so the first stars that emerged from this primordial material were very massive, something like 100 solar masses. And of course, big stars explode rather soon. So after a few million years, they exploded, and they seeded the first heavier elements, heavier than hydrogen and helium. And that changed the gas conditions of the universe, certainly locally. And so with more cooling possible now, you have more fragmentation, and you can make smaller stars, including subsolar mass stars. And those are the stars that we are trying to find when we search for the oldest, most metal-poor stars, as these guys have very long lifetimes. As you know, the sun has a lifetime of 10 billion years, and the little guys that we are chasing about 0.6 to 0.8 solar masses, and they have lifetimes of 15 to 20 billion years. So assuming that they formed soon after the Big Bang, so within about 500 million years, they are still alive and kicking, and will do so for a little longer. And that offers a chance for us to observe them and to study their chemical composition, because that tells us about the conditions of the state of the gas in terms of the chemical composition when they were born. And then, of course, you know, more and more generations of stars formed. More and more of all the elements was made, and here we are today. To summarize that in this little movie here, which becomes also relevant for the second half of my talk, I'm going to show you this dark matter only caterpillar simulation, where you can sort of see what I just mentioned. I want you to look for the red dots and the yellow dots, so the sites of the first stars and the first galaxies, and how they come together to eventually make it in, or many of those make it into the Milky Way. And these are the little dwarf galaxies that we are trying to catch and then study. So I'm going to start this, and you see these little colored dots, red and yellow, basically everywhere, and many get incorporated into the Milky Way, the white circles, the virial radius of this Milky Way sized galaxy there. And you can see how it all, you know, it's the beehive. You've all seen it many times before, but again, the point here is that we are trying to look for these dwarf galaxies, as they can tell us about these very early star formation sites. Now, I want to just spend a moment on chemical evolution, because that is sort of the outset for how we find old stars. If you imagine this pink or purple cloud there to be the primordial universe, then the first stars formed, they fused some elements in their cores, they exploded as supernovae, the massive ones at least, and then all the newly created elements were put back into the reservoir, and then you repeat this cycle again and again and again, and over time the amount of elements, of all the elements, will steadily increase, and that has as a consequence that stars that formed more recently will contain a larger amount of metals, than the oldest ones. And so we chase the stars that have formed once the cycle had only gone around a few times. And so the small amount of metals indicates that the universe simply hadn't made much of that material yet. And I'm a spectroscopist, so you can see a bunch of spectra there. The sun is at the top. Lots and lots of lines. That is not noise. This is all elemental lines, all overlapping, very complicated to work on. Claire knows all about this. Once you dial down the metallicity, so you go back in time, you can see that the spectra clean up quite nicely. Now there's noise in the bottom 3 spectra, but you can still clearly see what's a line and what's probably noise. And then if you go to the bottom star, we think that that's a 2nd generation star, low mass 2nd generation star. You can see only one small iron line there at 3860. And that one has an iron abundance corresponding to -5. So that's sort of the full range, or almost the full range. We have one star that has no iron lines, so that has an upper limit of -7. But this is one very low one that has still something detected. And to summarize this part here, what we call stellar archaeology is when we take these low mass stars that we find in our own galaxy, we take them to the telescope, get spectra, we determine the chemical composition of the atmosphere, so the outer part, and that in these hydrogen, so these little guys are still burning hydrogen to helium, and the outer parts have not talked to the center, so they don't know what's happening in the core. And so the outer parts are exactly the material with exactly the same composition as the star-forming cloud from which they are formed. And so we have this opportunity to use these stars as tools to study the chemical composition of the early gas clouds. And just in terms of definitions, you'll be seeing the iron over hydrogen bracket notation a bunch here and there, and I hope you're all familiar with that, but the -3 number is sort of a magic cutoff for us, because once you go below 1,000 of the solar iron abundance, you're technically in a regime where that iron and also other elements come from only one event. So everything below -3 is sort of has a large possibility of being early generation. So could be 2nd generation, but certainly one of the earliest generations. So either one prior first star that produced all that iron in their supernova, or when it comes to heavier elements, one specific nucleosynthesis event is enough to create abundances found in these stars. And altogether, this hopefully highlights to you that these galactic metal poor stars are a great tool for near-field cosmology, because they are the local equivalent to the high redshift universe. So they are really just around the corner in the halo, in the cosmic corner. And we have this chance to directly study this early time in terms of the chemical composition. Now, here I have used low mass stars as an example, but I want to extend this now to dwarf galaxy archaeology, where we take not just individual stars found in the halo, but we take entire dwarf galaxies, and specifically the very faintest, the ultra faint dwarf galaxies, and many of them, of course, been discovered in Cambridge. So I don't actually find dwarf galaxies myself. I try to find stars or discover more about the stars in them. But as it turns out, you can just use, rather than just one star, you can use an entire galaxy also as a unit to study the conditions at early time. And I'd like to highlight this approach by means of 2 examples. And here they are. So this is a plot of all the, it's not super updated, but shows a whole lot of the dwarf galaxies discovered in the last 20 years or so. And at the bottom there, you will see Tucana II, TUC II, and Reticulum II. I'll be talking a little bit more about those now. I won't have time to go into all that much detail, so you might need to ask me some question or shoot me an email, but I just want to give you a sort of a feel for what can be done with these individual galaxies by showing you, example of two contrasting ones that nicely illustrate this concept of dwarf galaxy archaeology. Before I do that, just a couple more introductory slides to dwarf galaxies. As you've seen, many are known by now, and altogether, even though each individually has not so many stars studied, but if you throw them all together, it's a good sample by now. In this review here by Josh Simon shows the metallicity distribution function of all the stars in ultra-faint dwarf galaxies, and you can see they're clearly metal poor. So these are metal poor galaxies full of metal poor stars. And more importantly, I want to highlight specifically that these galaxies are lacking the metal rich stars. That's why they are so full of metal poor stars, right? It's always in relative terms. And any bigger galaxy would have a tremendous number of stars at high metallicity, but these guys are lacking this. So hardly anything above minus 1.5. So that's important to keep in mind for later. And here's the metallicity luminosity relationship. That's also quite important. You can see there's a clear trend, more scatter there at the bottom end when it gets to very faint galaxy luminosity. So these systems at the bottom end only have a few thousand stars. You basically turn one bright star on or off and you've changed the luminosity of the galaxy. But you can see the fainter they become, the more metal poor they become, because they're lacking more and more of the more metal rich stars. So that just is stripped away. And from independent works, it's known that they are quite old, so that goes along nicely with their low metallicity. On top of that, they're all dark matter dominated. That's what makes them dwarf galaxies or galaxies in the first place. And I will come back to that very point in, I think, my last slide. Yeah, so this bottom end is obviously very interesting to me when you, I already mentioned this magic cutoff, -3 in iron over hydrogen, and my chi by I there, this red bar ends right at -3 there. So can we find galaxies that have an average metallicity of -3, right? That's perfect hunting ground for folks like myself. There are a few more technical problems that go along with it, but I'll just leave it at that. So these little guys are really nice when you like metal poor stars. I think that's quite obvious. All right, so here's my overview. As I said, I want to chat about two galaxies, Reticulum II, the first known R-processed galaxy that my former student Alex G and I found back in 2016. It's a bit older, but it remains a really good story, especially in contrast to Tucana II, the other system, which was only just published. And that seems to be by far the most extended ultra-faint dwarf galaxy. And so there are interesting stories that go along with those two that I'd like to share. And that work was done with my student Ani Chidi. Actually, he just graduated today. Actually, during my talk is his online graduation ceremony, which I'm missing now. But he gave me his okay, and he's going to be a Princeton Fellow in Chicago. And actually, Alex is also going to Chicago. Seems like I'm supplying the stellar archaeologists to Chicago now, but that's okay. All right, so Reticulum II was studied and confirmed by Simon et al. 2015. And as you can see from this color magnitude diagram there on the left, there are a few stars. The red ones are the confirmed members that are brighter than sort of 18.5 or 19th magnitude. And that regime can be accessed with high resolution spectroscopy. One of those spectrographs, the Mike spectrograph, is sitting in the left clay telescope that you are seeing there in the little movie that I'm just showing you to show you the Milky Way and to distract you a little bit. So back in the day, we observed the 9 brightest stars in Reticulum with Mike. And this is the data that we got. Now, these are faint stars. The weather wasn't great. And this is the crummy data that we got. But you're going to notice 2 important things. Let's start on the right with barium. The bottom and the top spectra are comparison spectra. The top one is another dwarf galaxy star. The bottom one is a strongly R-process enhanced halo star, which means it has strong absorption lines from all the heavy elements heavier than iron, including barium and europium, which you can clearly discern there at the bottom. And then the 7 of the 9 spectra in the middle also show a strong barium line, despite the fact that the data is really noisy. And then if you know what you're looking for, you want to see the same thing on the left. Most spectra have something that resembles a line, or certainly some absorption at that position, but 2 stars do not have that. Now, that meant, okay, we probably found a dwarf galaxy that had some R-process event going off. And I want to define that a little bit more. So the R-process, unfortunately, I don't have time to go into much more detail, but it's this nucleosynthesis process that through neutron capture produces all the heavy elements. The site, the astrophysical site, has been debated ever since the 1950s. And the candidates are core-collapsed supernovae, so above the proto-neutron star, because there you would have a strong neutron flux that you need. Neutron star mergers, of course, lots of neutrons to play with, and other type of exotic supernovae. And me and my colleagues have been interested in figuring out the astrophysical site for a while. And as it turns out, Reticulum II was an ideal target to learn more about this. And associated questions with that are, of course, what the rate and the yield of the event are, and is the dominant site changing over cosmic times. So let's try to answer this. To cut a long story short, let's look at the abundances first, because this is what I'm primarily presenting today. You can see here in blue a pattern. This is the so-called R-process pattern. So abundance is on the y-axis, atomic number on the x-axis. And this neutron capture process always produces the element in the same ratios. And that looks exactly like this pattern. That has been extracted for the sun. And we see that in all the R-process stars that we have by now found in the halo. There's often a shift, a vertical shift that goes along with metallicity. And so the overall amount might be different, but the ratios are always the same. And you can see here in red, this was the first very famous R-process star, CS22892 minus 52. You can see that the red points overlay with the blue curve pretty well. So the blue pattern is not a fit to the data, it's just overlaid to show that the stars always have this kind of pattern. And so this was the first thing that we had to do with these reticulum stars after we saw that, oh, there are barium lines and europium lines, when we actually had not really expected those. All other stars in all other dwarf galaxies had really low barium values, unusually low actually compared to halo stars. And europium was usually not even measurable. And so here is the result in black. You can see the stars from Reticulum. In purple is this R-process pattern, and the data matches. The gold curve is the S-process, for those of you who like to know a little bit more, but that's another process that can also make all the heavy elements in different isotopic distributions though. And you can see that's the main takeaway message here, that the gold pattern does not match the data. So we found ourselves a galaxy that contained a lot of R process stars. And here's a more common depiction of abundances in our field. We have some abundance ratio on the y-axis against iron on the x-axis. And here it's just shown barium over hydrogen and europium over hydrogen. And you can see in red, these are the R process reticulum stars. The in gray, you have the halo stars, and you can see the red ones overlap with this little fuzzy cloud of gray halo stars. These are the other R process stars. And then the colored ones at the bottom, the upper limits, those are the other dwarf galaxy stars. As I said, they had unusually low values, and this is what we expected. Instead, we found the bright red dots orders of magnitude higher. So that was very exciting. And that, as I said, offered an opportunity for us to use now the entire galaxy to ask a few questions of this early formation process. But first, we did a pretty simple game. At the time, we had, there were 10 ultra-faint dwarf galaxies known, more by now, but I like to stick to this very simple calculation here. And so we had 1 out of 10 R process galaxies, which meant in 1 out of 10 systems, 1 R process event had gone off prior to the formation of the stars that we have observed. And then you can make a back of the envelope calculation for how many supernovae we would have expected to have occurred back then in that entire population of ultra-faint dwarfs, and it comes out to about 2,000. So we have a rate of about 1 per few thousand supernovae, right? That's actually a pretty good guess. I'm still hoping, I've had this line in there for a while, LIGO will deliver in 2+ years. With every year it keeps being that, but I hope ultimately we get a really good rate by other means so that we can compare this. And our number has of course also changed a little bit more, and I'll come briefly to that in a little bit. So we have the rate down. How prolific might this event have been? So what is the yield? That's the big question. Here is the key now. That's why having found R process stars in a dwarf galaxy is so much more valuable than finding individual ones in the halo. Because if you remember the initial movie, you saw that the yellow and the red star formation sites were coming together into the halo, right? And these R process stars, they are probably, descendants of that, which means they formed in a dwarf galaxy far, far away. That galaxy was then gobbled up by the Milky Way. And now these stars are in the Milky Way, but they're not of the Milky Way. So we cannot really derive in any way how these stars formed and what the conditions were. But finding these stars in a dwarf galaxy now does allow us to bracket, as you can see here, the gas mass, make an educated guess about the birth conditions. And we're taking here 10 to the 5 solar masses as sort of the minimum gas mass for making stars, which also is this swept up gas mass from any kind of supernovae, because of course there would have been supernovae in Reticulum II. And then the maximum mass we take 10 to the 7, which we guess is the total mass of the galaxy. So still a factor of 100, but so much more information than what we had before. And then you can do, of course, a quick back of the envelope calculation. You mix the yield of a neutron star merger or a supernova or your exotic supernova into, and we used here 10 to the 6 solar masses of hydrogen gas, and the yield we took as 10 to the minus 4.5 for europium here as an example. And then you can get your europium to hydrogen abundance out. And it turns out to be minus 1.2. This number doesn't mean much on, without context. But here is the context. So europium is on the right. You can see minus 1.2 is smack in the middle of this orange bar that you're seeing there. It's plus minus 1 that depicts the gas mass uncertainty. This is a logarithmic plot here. And so that actually overlays broadly the red points that you can see there. So it's quite plausible, given this little exercise, that something with the yield of a neutron star merger would have exploded or gone off prior to the formation of these stars. Now I want to make the point here, and then, I should say that you see the same for barium, just slightly different numbers, but also roughly matches with the data. And the other point I think that's important to make here is that you see I have the brown bars there as well at the bottom. Those go back to supernovae. Their yield is 1,000 times less than that of a neutron star merger. And so it brings you down 3 orders of magnitude, so 3 decks. And you can see it's actually fairly agreeable with the data from the other dwarf galaxies. And I want to reiterate an important point here. Of course, all of these systems have supernovae go off. The question is the R process in full swing operating in these supernovae? And the answer here is clearly no. And I'll have an additional supporting argument on the next slide. But it is the case that sort of a wannabe R process might well be operating in a supernovae, so that a little bit of strontium and a little bit of barium and a little bit of europium is maybe made, but not in this full-blown fashion as the R process usually operates, that produces this characteristic universal pattern that I have shown you. So I think this, what you can take away from this slide here is that, yes, there was a prolific event. That could be consistent with a neutron star merger, but I think it also really nicely shows that supernova do play an important role in providing small amounts of heavy elements to a given system at early times already. Just for completeness, the jet-driven supernovae are mostly a theoretical concept with also some yields published. If you add those, they're not so unlike that of these neutron star merger yields, so they could also be possible. And by now, they're rotationally driven supernovae also discussed. So my personal bet is still that it was a neutron star merger that went off, but I cannot exclude that it was something else as prolific as this here, this example shows. Yeah, so the pundits might say, like, well, why don't you just increase the number of supernovae to get a higher yield, right? You would only need 1,000 supernovae to make up to a more prolific, or to build up a more prolific yield. But that is again where the nature of the dwarf galaxy comes into play, because no, you cannot just add 1,000 supernovae to that little system. It would have blown it apart. And because it is surviving until today, we know that is a constraint that cannot be changed. And so that really rules out supernovae as core collapse, ordinary core collapse supernovae as major R process producers. And another concern is, well, wouldn't a neutron star merger take way too long to enrich the galaxy? If we think back, I hadn't really pointed this out, but these are all very metal poor stars. They're very close to -3. And they must have formed very, very early on. And a neutron star merger takes time to inspiral. And so isn't that attention? That was attention for a long time. But as it turns out, there are more and more simulations of this coming up. And they're showing that it actually takes, the fastest ones are taking 50 to 100 mega years to coalesce. And of course, as I said, there were early supernovae in the system, and that meant some energy injection. And after you puff things up, it takes a little time to cool down. And that also takes about 100 mega years. And maybe that was just sort of enough time for this neutron star merger to do its thing before that next generation, the second generation stars, were formed. And by now, Reticulum is not the only R-process galaxy. Tucana III, not to be mixed up with Tucana II, that I'm going to talk about next, also has mildly R-process enriched stars. It's not, those stars are not as enhanced as the Reticulum stars, but there are indications now so these two ultra-faint dwarf galaxies, and also some of the bigger ones, that the R-process is definitely operating in these small systems. And I think the 14 is actually outdated, so it's like 15, 16, 17 stars now, as ultra-faint dwarfs now. So the rate is still, you know, about 1 in 10, give or take. But I hope that more dwarf galaxies will continue to be discovered, and so that we can test what this rate might be, because it does tell us something about the rate of this type of event. I just want to add that here for completeness, I'm part of the R-Process Alliance. That's a US collaboration of spectroscopists. We try to find more R-process stars in the halo, so very different in terms of the environment, as I already said, but nevertheless an important complement, because for the halo stars we can get really, really exquisite data, and we can study very fine details in, for example, the pattern. So we need to pursue both avenues in order to really make progress in identifying the astrophysical site of the R-process. So to answer the big question, what is the site? Well, definitely a rare and prolific site is operating. A neutron star merger is a very good candidate. Galactic chemical evolution models actually have trouble dealing with just one source. So they're all calling for at least 2, perhaps more sources. So I think this game really isn't over, although a very big first step has been made. And I should say, by the way, this was all prior to the first LIGO discovery of a neutron star merger. That certainly cemented that neutron star mergers can make the R-process, or that the R-process is operating there. So that was, of course, a very important result for us. But I think there's probably more, and so other types of supernovae, I think, remain a possibility, and there are multiple papers out there. One is coming out with David Young as a first author soon, so watch out on that. In terms of the rate and the yield, well, 1 per few thousand, and I'm listing a total R-process yield there of 10 to the minus 2.5 solar masses, and the dominant site is probably not changing over time. Well, let me be a little bit more specific here. There are probably neutron star mergers that occur at all times. We'll have to kind of see if that's true for the different types of supernovae as well. So I think there's more work that needs to be done there as well. All right. So that was the short story of Reticulum II. Now I'd like to share the short story of Tucana II. Just a reminder, the ultra-faint dwarf galaxies are very faint. You can see on the right there that in Tucana II, most of the stars are fainter than 21st magnitude. When you're a high-resolution spectroscopist, that's bad news. Because we can't reach there, we can hardly go past 19th magnitude, and you can see there from this probability coloring of the points that above my 21st magnitude, the probability of catching members is also fairly low. So if you want to study further away galaxies with fainter stars, you're kind of out of luck quickly to really determine what's actually part of the galaxy. So need some clever workarounds. Here's again a summary of what we can sort of reach with high resolution spectroscopy. Is just the top end. Not much we can do. With medium resolution you could go fainter, and but if you then go and do photometry in some way, you can reach almost all the way. And this story here is all about that, namely narrowband photometry that we have obtained to chemically characterize the stars in this dwarf galaxy, to identify members and features. Here's how this works. It's not new by now anymore, but the SkyMapper telescope in Australia has a metallicity sensitive V filter centered over the calcium K line in the blue. And a while ago, we got an auxiliary program approved besides the SkyMapper Southern Sky Survey. And we got separate pencil beam observations of several dwarf galaxies in all these filters, including the little V filter. And you can see in the top right plot there that metallicity really influences the flux through the filter. And the more metal poor, the brighter the star is, because there's less absorption. So for once, nature is throwing us a big bone here. And Ani's PhD thesis has been on this development. And you can see there one plot at the bottom that compares the photometric metallicities we got from this procedure compared to high resolution numbers. And the agreement is quite good. The sigma is 0.16 at -2 and 0.35 at -3. I think that's a really terrific result. So bottom line is we can get metallicities down to quite faint magnitudes from photometry this way. And here are my big questions for Tucana. What are the true sizes of the first of the surviving UFDs? Are they compact? Are they extended? Or are they stretched out even more? And the associated questions here are: how common are compact and extended systems, and what causes the different sizes? So let's see if we can answer that. Again, I have to gloss over a lot of details, but I just want to walk you through this. The most important point is that SkyMapper, because it was designed to carry out a large survey, has a huge camera with a huge field of view, 2 by 2 degrees. So when we did this these pencil beam observations of the dwarf galaxies, we got a lot of data for free. We didn't really want it, but we got it anyway. And then Ani obtained metallicities for everything in the images, because why should we cut them short? We can just process them all. And in addition, Gaia came out, and so it did some clustering analysis there, and you can see on the left that having proper motions available really helps to cut out interlopers. And then based on the metallicity and using the U filter to get some idea on the gravity that you see on the right side, there's also ways to cut out non-members. And so that allowed us to derive a new membership criterion and probabilities in a spatially unbiased manner, because we just use process the entire image. And until now, studies of dwarf galaxies had always been carried out with much smaller field of views, right, centered on the galaxy. And in the membership criteria, there was a spatial likelihood term added, because all ultra-faint dwarf galaxies looked quite small. I mean, they're wimpy faint galaxies. Why should they be big? So in order to help identify members, this spatial term was included. And that's what you see in the top row. But because we have these big data, these big images, we dared to remove the likelihood term, because by having the proper motion cut, the gravity cut, and also a metallicity cut, because I told you before, these systems are all lacking high metallicity stars. So if we have good metallicities, which we have, we can cut out the high metallicity foreground stars, or background stars even, I guess. Some, and because we trust our metallicities, and you can see that in the bottom row. The red circles were previously identified members. We recovered all of them, maybe except for one. And you can see there's this halo and cloud that surrounds that to quite large distances. And the question is, what is the galaxy? Is it the top or is it the bottom? I already mentioned that. And so just to highlight this, this was Tucana before 2018. This is at a scale of about 2 half-light radii, give or take. And then this work that Ani did for his PhD thesis yielded these additional members. So these were, we confirmed, so we took all the cloud stars, we observed them with medium resolution spectroscopy to make sure that there was something. And we confirmed them to be metal poor members, because then we got radial velocity. So these are all radial velocity members that we got from the spectra. And now they stretch out to 9 half-light radii. And I'm going to show you this one here again, just a slightly different depiction here at the bottom left. And you can now see the metallicity coding. All of these outer stars are extremely metal poor in right the sense of it. So they're even below -3. So we found 8 stars, and they're all below -3. And so the average of all these outer stars is -3.02, and the core population has an average metallicity of -2.6, and that equates to a total average of about -2.8. So this is one of the most metal poor galaxies out there, and it's really amazing. And you can see that this really translates even into this metallicity gradient that you can see on the right there, that the further you go out, the more it drops. And our lowest metallicity stars are around -3.5. And even in the halo, that's already quite an achievement. So finding that in here at 9 half-light radii is absolutely amazing. In case you're wondering, it looks like there's this weird S shape in the stars that we found. We worked with someone to model a tidal disruption, and that is supposed to go along these 2 arrows, and the stars do not go in the direction of the arrows. In fact, they are perpendicular to it. So we think that this is not a tidal disruption event that we're witnessing here, but something else. Not now. Wann gehen wir auf? Wie viele Minuten gehen wir? Gleich. Okay. Sorry about that. We've been thinking long and hard, if it's not tidal disruption, then what else could it be? And there are two options. One is sort of, I guess, heating by supernovae and some dynamical interactions. And here, that resulted in a separate paper. The other idea was realized in a simulation, namely, what if this Tucana II is already the product of a merger of 2 even smaller galaxies? All right, you've now witnessed both of my kids. I only have 2. So what you see here is a progression of the simulation where 2 sort of building block type galaxies, so some of the earliest systems formed are merging. They're separated, they're at 700 megayears, then it has sort of gone through the middle and shoots out on the other end at 7:55. Then at about 9:30, it kind of very fluffs out, and then in the end at 3000, it is sort of settled down, but in a much more fluffy configuration. And this was a simulation that wasn't specifically tailored to the case of TAC2. It was just a merging system in that box that we specifically looked at to see would anything in that reality of a simulation possibly be looking like what we're finding in TAC2. And then on the right side, you see that there's actually quite some star formation being triggered by this little merger, which is actually a major merger because of the similar masses, even though the systems overall, of course, are really tiny. So a lot of star formation being triggered, causing a large ion abundance spread, which is also what we're seeing. And then if you look at just at the stars formed during and after the merger, you can see there's a really nice gradient. And in red, the red stars are the Tucana observation sort of overlaid. We calculated the 2D distance and then the metallicity. And there's a remarkably good agreement, and there was no fine tuning involved. Of course, into any simulation, there a number of prescriptions go in, but we didn't do anything that we wouldn't have done there or anyway. And it seems to be matching the situation with TAC2 pretty well, which makes us think that TAC2 is probably the product of one of the earliest, perhaps the first galactic mergers, and ultra-faint dwarf galaxies by extension are not the building blocks the analogs of the surviving building blocks. So they are probably already assembled systems themselves. And that is principally supported by other theoretical works like Mark et al. Saying that U of D should have 1 to 4 progenitor systems. And so it's nice to have found an example where that seems quite likely. And so I bet that extended halos are not uncommon. And we will do more work to try to apply this technique to other systems to find out more. In closing, I'd like to add one additional point here, because we now have an ultra-faint dwarf galaxy that has stars out to 9 half-light radii, which means it's actually an ideal target to measure the mass, the dark matter mass, because the extrapolation doesn't need to be as extreme as it usually is, right? So stars are measured just within 1 or 2 half-light radii, and then it's extrapolated all the way out to get a mass. And now here we have 9 half-light radii. And so we did exactly that. The farthest bound star is bound. It has a perfect radial velocity. There are some other arguments. And the mass within 1 kiloparsec, so that guy sits at about 1 kiloparsec away from the center, really quite large, is 1.3 times 10 to the 7 solar masses. And you can compare that with just generalizing an NFW profile out to 9 half-light radii, and that comes out about 2 times 10 to the 7 solar masses. So it's roughly consistent. That, of course, suggests then that the total halo mass would be 10 to the 8 solar masses all the way out, which is consistent with the masses suggested for atomic cooling halos, which have been suggested to be the first galaxies. So I think we're very much in this regime of the first galaxies, and Tucana II is a wonderful example of a surviving relic from this very early time. So to answer the big question here, probably there will be ultra-faint dwarf galaxies that are compact, but definitely not all of them, and it will require more work to really answer that question. But I think it will probably very much depend on the merger rate that we could possibly get from additional simulations of these early galactic blobs. And then we'll see if that translates to the observed fraction once we have that. There are definitely extended systems out there. Tucana is just the first example, but I can feel it in my toes that there will be more. That's all I can say right now. And they're probably the products of these early mergers. And I'm wondering if, depending on the merger properties, if there are systems that are even more extended, maybe actually Tuc II is even more extended, we would need to have even wider sets of images to truly answer that question. So I think that's definitely on the books now as well. And as I said, we definitely need a larger box in terms of simulating these early blobs, and also run them for longer times to see what they do long term. If they kind of, jumpstart star formation again, or some of them, or if they're just kind of quiescently sitting there for forever after this early merger. And I'm eager to learn more about the merger properties and also local energy injections, because again, supernovae are always in these systems, so they always play a role and they will always tell us something. And I think we now have found a way to see the effects of that, possibly in the nature of the extendedness, once we can tell that for the entire population of ultra-faint dwarf galaxies. That brings me to my summary. I think the future is here in the sense that the dwarf galaxies have really been proven over and over again to have enormous potential for studying the early universe. I told you a little bit about the R-process galaxy Reticulum and the very extended galaxy Tucana II. I hope that more dwarf galaxies will be discovered. I cannot believe that we found them all. Of course, I'm also hoping for bigger telescopes so that we can catch up a little bit with high resolution spectroscopy, because I definitely want to know what the detailed chemical profile of these extended outer stars looks like, but I might just need to wait a little bit longer. So with that, thank you so much for your attention, and I'm happy to take questions.